The simplest is visit all states and traverse all transitions. And that's minimal coverage criteria for a state diagram. Now, if you've got a table which provides for both valid and invalid combinations of states and events, then the coverage criteria for a table is all rows in the table are covered. Now, that tends to be something that's difficult to achieve in practice because in many cases you find that there are certain state event combinations that you simply can't make happen. But the idea is to try to make them happen through your testing. And then there is the transition sequence of some length n. So visiting all states and traversing all transitions covers all transition sequences of length 1. But we could also say, well, we want to cover all possible transition sequences of length 2 or length 3 or length 4 to try to see what happens when sequences of events occur. So we'll look at each of those three. Now, what are you trying to test with these state techniques? Basically, there are two things you're looking for. One is, does the wrong action occur? Okay, the system just does the wrong thing based on the state that you're in. Or does it perhaps do the right thing, but then all subsequent actions are wrong, leading to a conclusion that perhaps it got into the wrong state. Now, of course, if it exposes to you directly what state it's in, you can see that it got into the wrong state at the end of the test, right? Otherwise, again, you have to kind of infer it by the immediate action was correct, but then subsequent actions were incorrect. Okay, so here is an example of a state transition diagram. Those of you who've gone through the foundation program will remember this perhaps, but I'll go ahead and refresh memories. In many cases, state diagrams have an initial state. So this is the state in which the activity starts. And in some cases, they'll also have a final state. You see the indicators here of the initial and final state. Now, in some cases, applications don't really have a final state so much as they have what's called a quiescent state, which is the state that they return to. So you can think of Word or PowerPoint as being that way. Once you've gone through a process of populating a dialog box or selecting a font size or font off of the menu, then it goes back to just the main screen display, right? Like for example, if I were to exit out of the state I'm currently in PowerPoint here, which is the presentation mode, it would go back into the standard mode where I would see the menu across the top, right? And then I'd see this slide, and then underneath this slide I would see a little notes section, and then on the left-hand side I would see the outline of the different slides that I could present next or edit next, right? And that's the quiescent state of it, the home state. So in some cases, applications, especially applications that don't have any sort of termination other than that which is perhaps forced by the user, will just have that quiescent state. An ATM would be another example. If you draw a diagram for an ATM machine, right? I mean, it basically is waiting for a customer. That's its quiescent state. And when a customer comes up, it goes through a sequence of states interacting with the customer, and then it goes back into that quiescent state. But in this particular example, what we see here, and this is an example of a state diagram for an e-commerce application, we're showing the application and its states from the point of view of the customer as opposed to the point of view of the e-commerce system itself, right? So from the point of view of the customer is doing something. It's not of interest to the e-commerce application until the customer comes to the website in question. So at that point, the customer is browsing, right? And they can continue to browse by clicking a link, and then the item is displayed, right? So the click link, notice this is the event, it's external to the system, right? Because it's the customer is doing it. And the system is going to wait until that event occurs, the link is clicked, and then it is going to display the item which was clicked. So that's the action. The arrow here is the transition, and notice in this case it's a transition from the browsing state back to the browsing state. Now you might say, what's the point of that? Well, the point of the transitions, these loop transitions, is that an event, when it occurs, has to result in a transition. That's how the diagram shows the handling of that event, right? And an action has to be associated with the transition. So even if we're going to be back, we're going to end up back in the same state, we still need to handle it. Okay, now, someone might decide to add something to the cart, as we see here. So then there's going to be a selection dialog that's going to come up, right? That's the action that the system takes. And now we're in a selecting state, and we're going to continue selecting the number of items, and form of shipping, perhaps, or whatever. And then having done that, we can, as the customer, choose to continue shopping, in which case we go back to the home page, presumably, and the browsing continues. Or alternatively, we can, from the selecting state, go and say check out, and in that case there's a login dialog that's going to pop up, and now we want the user to log in. I'll also point out that at any of these states, the user, of course, is free to simply abandon, in which case they've gone into this state where they have left, and that's the final state from the customer's point of view, right? They've abandoned the transaction. That can happen also here. Okay. Now, in logging in, we can log in with a bad user ID and password combination. There is an error message that's displayed. Notice here's the condition, because the same event, log in, if the username and password combination is good, will result in the display of a purchase dialog. Now we're in a purchasing state. And similarly, we have a condition here. If in the course of entering information in the purchasing dialog, we enter bad information such as invalid credit card number or invalid address or something like that, we'll get an error message and remain in the purchasing state until we have cleaned that up. Unless, of course, mid-purchase we decide to abandon. If the purchase information is all good, a confirmation screen comes up, and the order has now been confirmed, and the user here can choose either to go elsewhere or perhaps resume shopping. Okay, so that's a nice compact way of describing the behavior of this system. Notice that the verbal explanation of the things that happen was fairly extensive, and if it were to be in text form, could very well span a couple pages of the document, requirement specification, for example, and it would be difficult from inspection to know whether something had been left out. There's the diagram, and you can look at it and verify by walking through it as we just did. Yep, sure, everything is there, everything that needs to be there is included. Or you might find that it's not, and then something can be added to the diagram. Okay, so how do we derive tests? Well, to achieve the basic state and transition cover, derivation of tests is fairly straightforward. What we want to do is, first off, adopt a rule about where the test must start and where it may or must end. So you could say that the test must start in an initial state and may only end at a final state. Now, the distinction there between may and must is that in the case of may end is that if you could go into that final state, and if there's a way out of it back to some other previous state, you could loop back and the test could continue. The test must end when it enters a final state. That means that that test has to end there. Okay. It's important to have these rules about what constitutes a test in these cases because with the possibility of looping, then the test could be of arbitrary length.